Welcome to This Explainer. Have you ever wondered how a solid, rigid piece of metal can just bend without snapping in half? Well, today we are bridging that exact gap. We're going to logically connect the dots between single dislocation theory at the microscopic atomic scale and the macroscopic yielding we actually see in everyday materials. So let's jump right in. Here's our roadmap for today. We're covering 4 key areas: the scale of macro deformation, the multiplication engine, obstacle navigation, and finally, solid solution mechanics.
So, starting off with part 1, the scale of macro deformation.
Okay, picture this. Imagine a perfectly defined physical space, just a simple cubic single crystal that's exactly 1 centimeter cubed. Inside this little cube, we have a Burger's vector of about 1 angstrom. Basically, that's our baseline atomic shift. Now, here's where we hit a bit of a paradox. If just a single edge dislocation passes all the way through this 1 centimeter cubed space, the resulting shear strain is an unbelievably tiny 10 to the negative 8th power. I mean, that is practically 0. So you got to ask yourself, how on earth do we actually get visible macroscopic deformation from such insignificantly small microscopic movements? Well, let's look at the physical reality. In the real world, dislocations frequently form nodes, or they completely annihilate each other before they ever cross the entire crystal. Because of this, our macroscopic strain equation has to logically account for this partial transit. We absolutely cannot just assume that every single defect travels neatly from one edge to the other. To solve this problem, we introduce a really critical variable, dislocation density, which we represent with the Greek letter rho. This basically means our overall strain is now evaluated as a direct function of this density multiplied by the average distance those dislocations actually moved. So we're shifting our entire perspective from just counting individual lines to looking at a whole localized population. And by differentiating that strain with respect to time, we get something truly beautiful, the Taylor-O'Rowan equation. This equation is the fundamental mathematical bridge connecting that atomic scale behavior directly to the observable material yielding we see with our own eyes. The crucial takeaway here is that the macroscopic strain rate is entirely governed by the moving dislocation density and their microscopic velocity. But wow, the math presents a pretty staggering reality. To achieve just 1% macroscopic strain in our little 1 centimeter crystal, the equations say we need 10 to the 8th power dislocation lines per square centimeter. Guys, that's 100 million lines. And for 10% strain, we literally need 1 billion. The crazy thing is, materials simply do not naturally contain this massive active army right after casting. So where exactly are they all coming from? That brings us to part 2. The multiplication engine. Enter the Frank Reed source. This is an absolutely brilliant mechanism discovered back in 1950. It starts off pretty simple, with an active dislocation segment that's pinned down at 2 points. Let's call them A and B. Now, this pinning usually happens because of nodes within the greater dislocation network, or sometimes just little clusters of impurities that essentially drop an anchor on the line and hold it in place. So as shear stress is applied to the material from the outside, this pinned segment physically starts bowing outward. Think of it kind of like blowing a soap bubble through a wand. The applied stress directly dictates its radius of curvature, so the harder the push, the tighter the curve. Now, the really critical threshold hits when the dislocation bows out so far that it forms a perfect semicircle. At this exact geometric point, the required shear stress, just to keep it moving, reaches its absolute maximum. You can think of this as the ultimate tipping point of the entire mechanism. And once that tipping point is crossed, boom, the loop expands completely spontaneously. But because it's still firmly pinned at points A and B, the expanding line has literally nowhere else to go but to curl right back around its original pinning points. This creates a very distinct kidney bean shape. As those two spiraling inward segments inevitably crash into each other below the pinning points, something super fascinating happens. Because they have opposite line senses, which basically means they have opposite geometric signs, they just annihilate each other purely upon contact. They just zip right together. And what's left behind is a closed, completely detached outer loop that just keeps expanding outward. Meanwhile, the original straight segment we started with is perfectly recreated. This precise geometric process repeats infinitely. It is literally an infinite factory, just churning out the millions and billions of concentric loops that are strictly required for macroscopic plastic deformation. So the math is finally satisfied. Moving right along to part 3, obstacle navigation.
Now, the reality is, crystals are not just perfectly empty spaces. As these dislocations navigate through the matrix, they inevitably hit structural walls, things like grain boundaries. And when they do hit them, they pile up. This massive pileup exerts incredibly concentrated forward stress on that poor lead dislocation at the very front of the line. But at the exact same time, it generates this back stress that actually repels any new dislocations that are trying to join the pileup from the source.
So, how do they actually get past these walls? Well, it completely depends on their type. Screw dislocations pull off this maneuver called cross-slip. They essentially shift gears, jumping to an intersecting plane to just bypass the roadblock entirely. Edge dislocations, on the other hand, are a bit more constrained by their geometry. They rely on a process called climbing. They literally move up or down a plane by absorbing or emitting atomic vacancies to effectively step right over the obstacle.
Which brings us to our final section, Part 4, Solid Solution Mechanics. You see, obstacles aren't just macroscopic walls like those grain boundaries we just talked about. They're also microscopic point defects. Because solute atoms, which are basically impurities purposely added to an alloy, distort the crystal lattice around them, dislocations are actually physically attracted to these defects. They do this to relieve their internal strain energy. So they all condense together to form this sort of impurity cloud or atmosphere, completely wrapping around the dislocation line.
This continuous pinning and unpinning effect, right, as dislocations physically tear themselves away from these clouds, is a primary mechanism of what we call solid solution strengthening. It's the direct cause of phenomena we observe on macroscopic stress-strain curves, like those really distinct upper and lower yield points, and the strain aging you commonly see in metals like body-centered cubic iron. So, to wrap all this up, we really need to recognize what we're actually seeing when a metal yields. Macroscopic deformation is fundamentally not just some continuous stretch like you're pulling a rubber band. Not at all. Rather, it's the rigorous statistical aggregate of literally billions of incredibly specific atomic scale defect maneuvers. So, the next time you're sitting at your desk and you idly bend a paperclip, ask yourself, are you just bending a piece of metal? Or are you actively commanding an invisible army of a billion atomic loops to navigate a microscopic obstacle course? Really makes you wonder, doesn't it? What other unseen forces are quietly shaping the physical world around us?